Good evening, students. Are you able to hear me?
Yes, sir.
Okay. So before I start this class, I have to tell you something important. So today's class, I am trying to record it in a high quality. Okay. For that, I'm doing a small experiment for which I need a cooperation. I need some cooperation from you guys. Thing is, when I'm explaining the concept, ensure you don't ask any questions. Once I complete the concept, I'll give you 2 minutes to 3 minutes time after every sub-concept. Okay, after every subtopic, I'll give you 2 to 3 minutes of time where we can discuss. So wait for the doubt session, and during the lecture time, please ensure that you're not talking. Okay, so that we'll be able to capture a slightly higher quality video. It's an experiment today. If it works, I'll tell you what is supposed to be done. I hope it is clear, right?
Yes, sir.
Yes.
Right. So we'll get started. So in the previous class, right. So in the previous class, we discussed the introduction to thermodynamics. We understood what is there in the branch of thermodynamics and physics, right? We saw certain basic terminologies that were associated with them, like thermodynamic system, what are the thermodynamic coordinates or state variables. Then we saw what is system and surrounding. Then we saw what is the boundary and the two types of boundary, which are diathermic and adiabatic, right? Then we went to the laws of equilibrium. In the laws of equilibrium, we have the zeroth law, or which is also called as thermal equilibrium, first law of thermodynamics, and we have something called as the second law also. Right? We saw what is zeroth law of thermodynamics. So zeroth law mainly speaks about the thermal equilibrium. What does it state? When there are three systems, if two systems are individually in thermal equilibrium with the third one, then the rest is also said to be in thermal equilibrium with each other. Right? Two systems in thermal equilibrium, the third system are in equilibrium with each other. Right? Similarly, important terms in thermodynamics, we saw what is equation of state. So equation of state is nothing but a mathematical equation which connects the pressure, volume, and temperature of a gas. Similarly, we saw what is an indicator diagram, right? Indicator diagram is basically a graph that is drawn between any two thermodynamic variables taken at a time. It can be either between pressure and temperature, it can be between pressure and volume, it can be between volume and temperature, anything of that sort, right? Then we saw what is an isothermal process, then we saw what is an isobaric process, isovolumic or isochoric process, and an adiabatic process. So what is an isothermal process? Isothermal process, the one in which the temperature of the system remains constant. What is an isobaric process? It is a process in which the pressure of the system remains constant. Similarly, what is an isochoric process? So isochoric process is the place where the volume of the system is said to be constant, and adiabatic process, the place where is a process where the exchange in heat of the system between the exchange in heat between the system and the surrounding is zero, right? Then we saw an important term which is called as work done, right? So when you talk about work done, we try to calculate it for both cyclic and non-cyclic process. So for a non-cyclic process, we understood that if the work is done, then under constant pressure, work is defined as P delta V, and under variable pressure, work is defined as integral of P dV from V1 to V2. Similarly, if you take the cyclic process into consideration, for cyclic process, we need to take the sign convention. And during that sign convention, we understood that work done is considered to be positive if work is done by the system. It is considered to be negative if the work is done on the system. Similarly, heat absorbed by the system is considered to be positive, and heat lost by the system is considered to be negative. For internal energy, energy increased is considered to be positive, and decreased energy is considered to be negative. So based on this, we understood that if the work is done in the case of expansion of volume, it is taken as positive. So W1 is a positive work and W2 is a negative work. When you try to calculate the total work in this cyclic process, you are going to get the area under this blue color shaded region, right? Then the last concept that we saw in the previous class was first law of thermodynamics. So what does first law of thermodynamics state? The amount of heat that you supply to the system will be equal to the amount of work done plus the increase in internal energy. Means the energy that you supply in the form of heat. So heat energy supplied will be equal to increase in internal energy plus increase in, sorry, not increase, plus work done by the system. So this is what is going to happen, right? So these are all the concepts we discussed in the previous class. Okay. So tell me, is there any doubt? Is there any doubt from the previous topics that you want me to discuss? Is everything clear? Now you guys can speak. Is it clear? You give me a confirmation, I'll proceed.
Yes, sir.
Yes, sir.
Yes, sir.
Right? Oh, okay, that's good. So please write down the next topic, that is specific heats of an ideal gas. Specific heats of an ideal gas. Okay. So here what is going to happen is, first, we know the definition of specific heat. So what does the definition of specific heat tell us? It is the amount of heat required to raise the temperature of one, or I can say temperature of unit mass of substance through 1 Kelvin, right? So this is the basic definition of specific heat. Now, the question that we need to ask is this definition good for gases as well? Right. So when you put this question, we can clearly say, yes, they work for gases also. Right. But there is another important question that gets raised when a gas is heated. Right. Basically, when you heat a gas, what is going to happen is its volume and pressure. Right? Its volume and pressure will change along with temperature. Now the question is, we don't know. See, we know one thing, that as soon as you supply heat to a particular gas, along with the change in temperature of that particular gas, there are two other parameters also which are going to get affected. Means volume will change and pressure can also change. So from this I can conclude the amount of heat. If I talk about the amount of heat required to change the temperature of unit mass of gas through 1 Kelvin is not going to be definite or fixed. Let's think about it. Why is this happening? Is because when you talk about the unit mass of the gas, then these two parameters can also change. They are also going to get affected, as a result of which there will be some other subsequent effects that will be taking place. Let's see one by one. Okay. So from this, the important conclusion that we are going to draw is, gases do not have a unique or single specific heat. Okay. So why doesn't it have? Because it depends upon the conditions under which the temperature change takes place. Okay, I'll explain this. Listen to this. Okay, what I'm trying to say is it is going to have multiple values, and all this is going to happen under different conditions. When I say different conditions, you can change the temperature of the substance under constant volume, or you can change the temperature of the substance under constant pressure. Anything of that sort can happen, right? When that is going to happen, then how does this effect take place is what we are going to see. So we know this, right? Already we know this from the previous chapter. C is equal to Q divided by M into delta T, which implies the amount of heat that you supply will be equal to MC delta T, right? So basically, this is the formula from which we can define the specific heat. Okay. First, I'm taking the adiabatic condition. So if I say adiabatic condition, I'm clear with the fact that the amount of heat exchange with the surrounding is 0. When that is going to be the scenario, observe this, no? C is equal to delta Q divided by M into delta T, which implies if I substitute delta Q is equal to 0, what am I going to get? I'll get C is equal to 0. Means it tells us that specific heat of a gas under adiabatic conditions is is 0. So let's have this in mind. Second, suppose there is an expansion or compression of gas taking place under isothermal conditions. Suppose it is taking place under isothermal condition, then I can say delta T is 0. Means I'll take C is equal to delta Q divided by M delta T. If I substitute delta T 0 here, I will get C is equal to infinite. Means the specific heat in this case is infinite. So here itself we got two values. We got a 0 and we got an infinite value also. Suppose there is a third condition where you supply heat. Okay, you supply heat to a system and the system is losing heat also. Okay, both are happening simultaneously. Means it's a diathermic process. There is an exchange of heat that is taking place between the system and the surrounding. If this kind of a scenario occurs in such a way that the supply of heat is less than the loss of heat, then what is going to happen? We can say that the change in temperature is going to be less than 0. It is going to be a negative value. So using the same logic, if I write C is equal to delta Q divided by M delta T, if I substitute the value here, I can conclude that C is going to be negative in this scenario. So what is the important conclusion that we can draw from here, guys? We are able to see that the specific heat of the gas can either be 0, or the specific heat of the gas can be infinite, or the specific heat of the gas can be negative, or it can be positive also. So having all these conditions in mind, we can conclude that the specific heat, this is only with respect to a gas, okay? Specific heat of a gas may have values between positive or negative numbers, ranging from where to where? Ranging from 0 to infinity. Okay, so this is the important conclusion that we can draw. Okay, so from this we can come to a conclusion that we use only two principal specific heats of a gas. That is, you will define the specific heat under constant volume, or you define the specific heat under constant constant pressure. Because when I talk about specific heat, I'm very clear that my temperature has to change. So you can change the temperature of the system either by maintaining the system at a constant volume condition or at a constant pressure condition. Okay. So this is the basic introduction with respect to specific heats of an ideal gas. What do these heats mean under constant volume and constant pressure? We will see next. Okay. Now it's your time. So do you have any doubts from the concept that I discussed till now? I'll show things to you. Just take 2 minutes time and let me know if there are any doubts. Okay. So is there any point you want me to repeat? Please speak, guys. Is there any point you want me to repeat? Nothing?
Sir, what is the case in liquids and solids?
Liquids and solids, it's going to be a different scenario, right? So that we already discussed the previous chapter itself. When we talk about the specific heat of a liquid, we saw what is going to happen to it. Like what is the case means? What are you asking? When you talk about the liquids and solids, generally what will happen, these parameters do not affect because the mass of the system is constant. You're only going to supply the heat to ensure that the change in temperature alone is taking place. So you don't have these many scenarios, right? You're able to understand. Whereas in the case of a gas, what is happening? Forget about ideal gas. In the case of a gas, what are all the things that are coming into picture? We're able to speak about the different types of conditions, right? Different types of state variables come into picture. What are the pressure and volume is also coming into picture, right? So I showed you. You understood what is the basic definition of specific heat. From that basic definition, if I try to apply what is going to happen with respect to a gas under an adiabatic process. Did you understand what happened under an adiabatic process? What is an adiabatic process? Basically, there is no exchange of heat taking place between the system and the surrounding. Then what are you going to say? Then it's called adiabatic process. Now listen. Now what does that mean by C being negative? Sorry, C being 0.
Sir,
what is the meaning of
is 0, sir. 0 joule.
So you are trying to supply some heat to the system, right? The system itself is present under what kind of a boundary? It is present under an adiabatic boundary. Means they're trying to say that whatever heat you supply cannot pass through this wall to raise the temperature of the substance that is present inside. That is the meaning of this 0. Okay. Similarly, when I say isothermal conditions, delta T is equal to 0. If I substitute it mathematically, it is telling me that C is equal to infinity. Infinite. It means they're trying to say you cannot define the concept of specific heat under this scenario. Correct. Similarly, there can also be a situation where you're carrying out the process in such a way that you supply heat, no doubt in that. Then there is a process of loss of heat also is taking place. Suppose there is a scenario where the loss of heat is more compared to the supply of heat, means the work is being done faster. Under that scenario, what will happen? Then the change in temperature is obviously going to be negative. Because what is the objective? Specific heat is mainly defined to increase the temperature of the system. But what is happening here? There is more amount of loss taking place compared to the amount of heat which is taken as input. In this case, C is going to be negative. Right. So this is the most important parameter that we are going to understand. So it can vary anywhere between 0 to infinity. It can be a positive number or a negative number. This is what happens with respect to whom? With respect to a gas. Right. So from this we can conclude that there are two principal specific heats of gas that we can confidently define. What are they? One is the specific heat under the constant volume, and the second is the specific heat under the constant pressure. Is it clear?
Yes, sir.
Right. Is any other doubt? Everybody is clear? Shall I proceed?
Yes, sir.
Perfect. So let's move on to the definitions. Let's try to understand the definitions of specific heat under constant volume. So it's very simple. As the name suggests, specific heat itself means amount of heat required to raise the temperature of 1 gram of a gas. So here I'm trying to define specific heat under constant volume for a gas, right? 1 gram of a gas through 1 degree Celsius when its volume is kept constant. When its volume is kept constant. So generally, it is denoted by CV. Okay. Generally, CV is used for 1 mole of gas. I'll come to that point. Okay. Here I'm talking about 1 gram. Similarly, what do you mean by specific heat at constant pressure? It is the same definition. The amount of heat required to raise the temperature of 1 gram of a gas through 1 degree Celsius at constant pressure. Okay. So generally it is represented with Cp. I'll come to that point as I told you. Right. So generally, when you talk about the gas, right, here, there is one more important point that we need to have in our mind. We spoke about specific heat. Generally, when you talk about specific heat, or the other name for it, which is specific heat capacity, you generally try to define it for the mass of a substance that is present. But generally, when you take a gas more than mass, we talk in terms of moles. That is why the more appropriate type of specific heat that we talk about is molar specific heats. Okay. So to differentiate, what we can do is, this Cp is there, right? This can be represented with a small c and a p, and this can be represented with small c and a v. Right. Similarly, when you talk about molar specific heat, you have the same concept, molar specific heat under constant volume, and you have molar specific heat under constant pressure. Okay, so when you talk about this, here this is written with capital C and a P, here it is written with a capital C with a subscript B. So let's try to define it. So what I'm trying to say is, instead of taking 1 gram of gas, if we take 1 mole of a gas, right, then the corresponding specific heat, is said to be molar specific heat. Okay. So having this in mind, we will try to understand the relation between these two parameters. Okay. That is, we will try to understand which parameter is greater than the other, and the mathematical relation that exists between them, which is generally given as Cp minus Cv is equal to R. Let's see it. Okay. So first note that you need to make is, Cp is always greater than Cv. Cp is always greater than Cv. Why it is so, I'll discuss it. Don't worry. Okay. The reason is very simple. So let's look at the reason for it. Now, when I say Cv, right, So CV means heat required to increase the temperature of 1 mole of a gas through 1 Kelvin. When this is going to be the scenario, listen to this carefully. Then from the first law of thermodynamics, from the first law of thermodynamics, which is written as FLOT in the acronym form. Okay. From the first law of thermodynamics, I'm clear with the fact that the amount of heat that I need to supply should ensure that there is an increase in internal energy taking place, plus some work is being done. Okay. Now, what is going to happen in this case is delta Q, can I write it as, so I know that delta Q is equal to, it is going to be mu into CV into delta T, where mu is going to be the number of moles and CV is going to be the specific heat, the molar specific heat at constant volume, and delta T is the rise in temperature. So if I write this here, mu into CV into delta T is equal to delta U plus, can I write it as P delta V? But what is going to happen here is, we know that whether you're going to write it as P delta V or integral of PdV, we are sure with the fact that delta V is going to be 0, because you're doing it under constant volume, and volume is constant, delta V is going to be 0, right? When that is the case, the work done in this process is 0, and we know the fact that mu is equal to 1. So when I substitute it here, I can say CV into delta T is equal to delta U, which implies CV is equal to delta U by delta T. That is another way of writing. Okay. So let us try to analyze both these expressions. When I write CV into delta T is equal to delta U, I'm trying to understand that CV into delta T is heat supplied and delta U is the increase in internal energy. So what I'm trying to, internal energy. So what I'm trying to say here is, in the case of molar specific heat at constant volume, the amount of heat that you're supplying is utilized only to increase the internal energy. It is not used to do any kind of useful work at all. So it is a very, very simple process. So in the case of constant volume, what is happening? The amount of heat that you supply is used only to increase the internal energy. It is not participating in doing any kind of a work. So due to which CV is going to have this value. Have this in your mind. Now, we will see what is going to happen with respect to CV. Okay. Again, from the first law of thermodynamics, I can say delta Q is equal to delta U plus P delta V, where P is at constant pressure, right? So delta Q is equal to delta U plus P delta V, but delta Q, can I write it as Cp into delta T? When I consider 1 mole of a gas, when 1 mole of a gas is considered, I will write delta Q is equal to Cp into delta T, which is also equal to delta U plus P delta V. Observe, this is not equal to 0. So what is happening in the case of the molar specific heat at constant pressure is, the amount of heat that you supply is utilized for two purposes. What are they? One is used to increase the internal energy, and the second is used to do some amount of work. As a result of which, what is the important conclusion that we can derive here is, the amount of heat that is supplied under a constant pressure condition is going to be more compared to the amount of heat that is being supplied in the case of constant volume condition. Because in constant volume, it is utilized only for one purpose, whereas in the case of constant pressure, it is utilized for two purposes. That is the reason why you can conclude that Cp is always greater than CV. This is a very, very, very important relation. Right? Now tell me guys, any doubt? Is there any point you didn't understand? So based on your silence, can I assume that things are clear?
Sir,
Please tell.
sir, can you show the slide?
Sure.
Sir, here,
Uh-huh.
sir, even though we are using the heat energy for only changing the internal energy, but in the second case, if the internal energy of the system is less, then the sum of internal energy as well as the work done is less than the first case, then what will happen, sir?
That will never happen. That will never happen because if you have a cylinder which is fitted with a piston, okay, you are supplying some amount of heat. Okay, if suppose this is a constant volume condition, okay, it is a C with the subscript V is not constant volume. Try to understand it is a molar specificated constant volume. It's just a symbol. So here, when it is going to be under constant volume condition, what will happen to this? This piston can never move up, right? Because its volume is constant. Means this whole thing is packed. So the heat that you supply is getting utilized for doing what? It will only keep increasing the internal energy. Okay. Whereas for the same 1 mole of gas, if I give a provision in such a way that this piston can be moved under a constant pressure condition, and you are supplying the same amount of heat, right? You are supplying the same amount of heat. That same amount of heat is doing what? It is increasing the internal energy of this. Increasing the internal energy is visualization. So what is going to happen is the particles inside will start moving with a greater velocity. I hope you're able to understand. Like how water boils, right? The particles start moving with a greater velocity. The same kind of a scenario is going to occur. Are you able to understand? And this piston will start moving the upward direction so that there is a change in volume taking place. That is P delta V. Correct? So this heat itself is utilized for what purpose? For two things. One is it is increasing this, at the same time it is doing some work on the surrounding as well. So which value will be more? For these two tasks to be attained, will you need to give more amount of effort to do two tasks or one task? You tell me.
Yes, sir. We need to
You're able
give.
to understand? Yes. That is the reason why Cp is always greater than Cp. Try to understand this. Okay.
Okay.
Here, guys, any other doubt? Any other doubt? So can I assume that no doubt? Can I proceed?
Yes, sir.
Now I'm going to derive the relation between Cp and Cv. So write down the heading. The relation between Cp and Cv. I want everybody to concentrate. This is something like this. Cp minus Cv is written as R, where this R is called as universal gas constant. Okay. So let's start the derivation like this. Let us take 1 mole of a gas and heat it under constant volume. So I'm heating it under constant volume. I'm clear with the fact that its temperature is going to change, so that the temperature increases by an amount. So the temperature increases by an amount dt. Okay, D capital T. Increases by amount D capital T. Right. This is the first step. Now, the heat supplied will increase the internal energy by a factor of dU. Okay, and we are clear that no work is performed by the gas because it's an isochoric process. No work is performed by the gas. When these things are taken into consideration, can I say that the heat spent in the process of increasing the temperature of 1 mole of gas is given as dq is equal to mu into cv into dt, where mu is 1. If I substitute, I can say dq is equal to cv into dt, right? But we know that this dq is equal to du. We know that dq is equal to du plus dw, but dw is 0. I can conclude that dq is equal to dw. So when I do this kind of an interchange, I will call this as equation number 1. Have this in your mind. Okay. Now the second scenario comes in. That is the heat. Now the second scenario is, now the gas, okay, now the gas which is of 1 mole be heated at constant pressure. Okay, let's say I'm heating it at constant pressure, that is P, through a temperature of dT. Now in this case, what is going to happen? If I say dq is the amount of heat supplied, if dq is the amount of heat supplied, then I can write dq is equal to cp into dt, since mu is equal to 1. Right? When this is the case, I will call this as equation number 2. So the amount of heat supplied is this much value, but what is this heat doing? The heat is also doing some change in volume, right? That is, it is creating some amount of work as well. So for that, how I'm going to write this? See, heat supplied will increase the temperature. Heat supplied will increase the temperature of the gas by dt and volume by dv. Let us assume like this. Okay. So now what will happen is, due to, can I say, increase in volume, gas will perform some work. So gas will perform some work, which is given by the formula dW is equal to PdV, which I call as equation number 3. Then from the first law of thermodynamics, I can say dQ is equal to du plus dW, right? So in this case, what is going to happen is the amount of heat that you supply, that is Cp into dt, will be utilized to increase the internal energy. Remember, internal energy is only a temperature dependent quantity. So it does not depend whether you do it under a constant pressure or constant volume. When that is going to be the case, then du can be replaced with Cv into dt. So this will be equal to Cv into dt plus this is going to be PdV. From this, we will rearrange the equation. So I'm going to rearrange the equation in such a way that Cp minus Cv into dt is equal to PdV. Let me call this as equation number 4. Now we know that from ideal gas equation, I can write PV is equal to N into R into T, but here N is equal to 1. So PV will be equal to R into T when I differentiate on both sides. Differentiate on both sides with respect to temperature. So when I differentiate on both the sides with respect to temperature, where the pressure is constant, don't forget that, then I will get P into dV is equal to R into dt. So what I'm trying to say is PdV can be replaced with R dt, which I will call it as equation number 5. If I use fifth one in fourth one, then I'll get Cp minus Cv into dt is equal to PdV is going to give us R into dt. So this dt and this dt will get cancelled. From this, I can conclude that Cp minus Cv is equal to R, and this equation is what is called as Mayer's equation. So this is the result you would have seen in your chemistry as well, right? Now, let's have the discussions. Okay, first, take some time to write it down. I hope you guys have copied it, right? Did you? Did you guys copy it?
Yes, sir.
Okay. So go through the steps. Is there any doubt that you have? Is there any doubt, guys? No doubt? Can I take the confirmation as no doubt?
Yes, sir, no doubt.
Right. So this is one thing. So then we can move on to the next concept. This will be the last concept for the day. That is work done in an isothermal expansion process. So we are going to discuss what is the work done in an isothermal expansion process. So when I take a PV graph, right? So when I say PV graph, it is a graph that is drawn between the pressure and the volume. Now the PV graph will be in such a way that this is going to be the scenario for an isothermal condition, because the condition is very simple. We know that PV is equal to nRT. When I say isothermal, T is constant, R is already a constant, and the number of moles for a closed system is also going to be constant. So from this we can conclude that P into V is constant. When P into V is constant, P is inversely proportional to V. When P is going to be inversely proportional to V, the important conclusion is as the pressure, so as the volume increases, pressure will decrease. So that is what is happening. So when the arrow mark is in such a way that it is in the increasing direction of volume, we call it as isothermal expansion. And this particular shape that you got is called as an isotherm. Okay, the shape that you have got is what is called as an isotherm. Now listen to this carefully. So when I know that PV is equal to constant, I'll call it as some K. When I call it as some K, my job is to find the work done. So I know that dW is equal to integral of PdV from V1 to V2. Okay. So when this is going to be the scenario, I know that PV is equal to N into R into T, which implies P will be equal to N into R into T divided by V. So I will take this and substitute it here. So dW is equal to integral of V1 to V2. PdV is N into R into T divided by V into into dV. Now what I can do is I can take that N into R into T outside, so that I will get integral of dV divided by V from V1 to V2. This will be nRT into integral of 1 divided by V is going to give us log V base E, where the volume is changing from V1 to V2. So here I would like to tell you one important point. When you talk about logarithm, so there are two kinds of logarithm which we talk about. One is called as common and the second is called as natural. So common logarithm is with the base 10 and natural logarithm is with the base E. So in your mathematics, whatever logarithm you're using is always with respect to base E. And the ones that you're able to see in the log book, right, that is with base 10. So nRT into log V base EC. Remember, log of x base E can also be written as ln x, which we read it as ln x. So what I will do is I will write it as ln from V1 to V2. Then this will be equal to nRT into ln V2, that is the upper limit, minus ln V1, which is the lower limit. So this will give us nRT into ln of V2 divided by V1, right? So when you write something like this, this can also, so let me call this as equation number 1. This is going to be the total amount of work that is done. Okay. A small correction which I would like to do here is this is the total work done. There is not small amount of work because I already put the integral. Okay, W is equal to this value, right? So this is the total amount of work done in the case of an isothermal expansion. Similarly, this can also be converted into common logarithm like this. W will be equal to, you need to multiply the natural logarithm with 2.303 nRT, then this becomes log of V2 divided by V1. If I write log by default, no, then it is log base 10. So try to understand the difference. This is also work done. This is also work done. Both are the work done in the case of isothermal expansion. The minute difference that lies here is, here we write it as ln, that is log base E, and here we write it as log base 10. Whenever there is a log base 10, that is, you convert log base E to log base 10, you need to multiply it with 2.303. Okay. The reason is very simple, because log of A base B can be written as log of A base C into log of C base B. Means you can introduce some other base like this and you can split and write it. That is one of the properties. So here what we did is log of x base 10, we wrote it as log of x base E into log of E base 10. Okay. So when you do this kind of a change, then this log of E base 10 is what is going to get converted to this value. Okay. That is what is 2.303. And that is the reason why you multiply 2.303 with log of x base E to convert it to log of x base 10. right? So, yeah. Any questions? Any questions, guys? This is an important derivation. Since this time it is descriptive, there is a possibility that they can ask you these questions. So be careful.
Sir,
Please tell.
sir, can you tell like how to find log of something using log table?
That is something, that's a different story that we can discuss on some other day.
Okay.
That I can tell you. You need to use that logbook and find it out. For that, you need to know the properties of logarithm, or else if I tell you something, you will not understand. Okay. Just remind me, someday we'll have a session on that. Okay. Apart from that, any doubt from this derivation? Is every step clear? Did you understand the physics and the mathematical part involved behind every step? Yes or no? Did you understand?
Yes, sir.
Okay. That's good. So that's it from my side for today. Okay. So revise these concepts. We'll discuss the remaining parts tomorrow. We can log off this.
Sir,
Yeah, tell me.
sir, tomorrow probably I might not attend the class, sir.
Okay.